Hello and welcome to another power electronics class. In the previous class, we spoke about the fundamentals of switches and what are the switches usually made of. You will usually build the switches from semiconductors. We had different type of switches, uncontrollable, semi-controllable, and controllable. And some examples of those were diode, um, thyristors for semi-controllable, and controllables are the transistors. And the transistors have different types. We have the MOSFET, uh, the BJTs, and so on. Today we're going to focus, today's class would focus on the steady state analysis of DC to DC converters. And also, if we have time, we will get deep into buck converters, boost converters, and buck boost converters. Before that, we will do a small introduction, which is a review of what we learned so far. So, to convert a DC to DC signal, we have different options. First option that we can use to convert DC to DC is simply to use a potentiometer, what we call a pot. A potentiometer is a variable resistor which we can change, and we can determine the output voltage by changing the voltage of the potentiometer. It uses the principles of the voltage divider, as you remember. So for this particular case, V out would be equal to R over, I'm going to call this RT, over RT times Vn, or Vg here in this case, V of the generator. And by adjusting this R, I can adjust the output voltage. But there is a big problem with this solution. Do you remember what the problem was when we solved power? Yes, power loss. About, in best case scenario, the efficiency of the system doesn't exceed 50%. 50% of the power would be lost, and it's going to be lost in this RT. It's going to create heat. Therefore, we need a big heat sink, and not efficient. It's going to be huge, costly. There may be some applications for this, but there are better options out there. So then we went to the second solution that we had. Second solution involves a voltage regulator. A voltage regulator is a combination usually of transistor, Zener diode. Also, a Zener diode is another option, which is a type of voltage regulator. And we usually have a feedback loop system, and we have a linear amplifier and a base driver, and we can regulate the voltage. As you remember from electronics, the most popular type of regulators, for example, was the 78 series, like the 7805, the 7 series. 7805 means this is a positive 5 volt, meaning regardless of the input, if the input is 12 volts or 100 volts, the output would be fixed at 5 volts or so on. Or if you have 7850 or a 50 volt regulator, the input is 100 volts and the output would be fixed at 50 volts. Again, the problem with this, in this particular case, you can see that the efficiency is around 50%, which is pretty low, meaning around 50% of the power is wasted in the voltage regulator itself. And voltage regulators, as you may remember, they look like this. They usually have a heat sink. I'm drawing the heat sink with black. And the reason that they have this heat sink is because of the amount of power it's dissipating as heat, which is wasting. And the bigger the voltage difference is, like this one is 50-volt difference, you need a bigger heat sink. Sometimes just a heat sink would not be sufficient. We need to add cooling systems such as a fan, air cooled or water cooled, something like that. Now we get to our third and most efficient solution is to use switching. And this is in the same example of a 100-volt to a 50-volt system. And by simply switching, and for this particular case, because we want to half the voltage, we want to go from 100 to 50, we can divide the switching positions or the switches in half, meaning half of the time in a second it's turned on, another half is turned off. We learned about the graphs of the switching. We have the duty cycle, which we call D, and we have the period or TS. TS is equal to 1 over Fs, as you may remember. And the equation for this was Vs is equal to dVg. And you can see that since if it's half the cycle it's on and other half is off, then the average would be roughly in the middle. So you're going to have, let's say, 100 volts in the output, in the input, and the output would be around 50 volts. So the duty ratio and the average value, the equation for the duty ratio, D is equal to T on over TS. So the ratio of when the switch is turned on to the total period. And V out would be equal to dVd. Right here we can write out V out as dVd as well. Both of them are the same. Now let's solve a couple of examples for this. If the frequency is equal to 2.5 kilohertz, and D is equal to 0.4, I want you to find T on. Did anyone? Perfect. So TS is equal to 1 over Fs. Therefore, period TS would be 1 over 2.5 times 10 in the power of 3 gives us 0.4 times 10 in the power of negative 3. Am I correct? Because 1 divided by 2.4 gives us 2.5 gives us what? Gives us 0.4. And 10 to the power of 3 goes to the denominator, will become 10 to the power. So it's equal to 0.4 milliseconds. And this is in second. Now, if the DO ratio is 0.4, then T on would be equal to the duty ratio times TS, which is equal to 0.4 times 0.4 times 10 to the power of negative 3 gives us 0.16 times 10 to the power of negative 3. Or in other words, it's 0.16 millisecond. Am I correct? Yes. Okay. Now the next question. If T off is equal to 4.5 milliseconds, so T off is 4.5 milliseconds, and T on is equal to 5.5 milliseconds. And Vn is equal to 5, let's say 3 volts. What is V out equal to? So again, this is 5.5, this is 4.5, and Vn, this is 3 volts. We want to find the average voltage, the V out. I'll give you a few minutes to think on it and solve it. And the first students to solve it gets extra points on their next homework. Hey, does anyone have the final answer? No? Okay. Give you a few minutes. Give you... 6.5? Yeah. Yes. Okay. So TS, which is the period, is equal to T on plus T off, which is 4.5 milliseconds plus 5.5 milliseconds. Because all of them are milliseconds, we don't. So it's going to be 10. D would be equal to 5.5, which is T on over 10, which gives us 0.55. And the output voltage, V out, would be equal to 0.55, which is D times 3, which is 1.65. What is the unit of D, by the way? So T on is in seconds and TS is in seconds. What happens is D doesn't have any units. Okay. Yeah, doesn't have any units. It's not in seconds or anything. It's just a ratio. Okay. Yeah. Is it clear up to this point? Okay. One thing that I wanted to add is that this that we just calculated, it gives us the average voltage. Okay. So the average power hour voltage here is here. But then what we see in the output is a pulsating DC. We know that the average is over there. But if you take a voltmeter and put it on R, and the voltmeter has very high frequency, like a oscilloscope, you can see the pulsating DC. So we need different components to add to this to make it smooth, so you can have a smooth output voltage. Now, part 2, we're going to study the basic topology of a DC to DC converters, which we have two main types. We have non-isolated DC to DC converters, like a buck converter, which is a step down, the boost converter, which is a step up, the buck boost, which is a step down, step up, and we have isolated DC to DC converters, which are the flyback, the forward, and the half and full bridge. So these are different categories, topologies of DC to DC converter, and we're going to start with buck and boost and so on. So buck converters. What is a buck converter? A buck converter is a step down converter. The voltage in the output is less than the voltage in the input. So V out is always less than V in for a buck converter. In best case, it's equal. And we also want to study its operation in steady state. So this is a normal buck converter. But the thing is, as I mentioned, if you measure the voltage in the output with an oscilloscope, you would see a pulsating DC. So what first thing that we need to add a storage system to be able to store the voltage so we can smooth out the voltage. Also, the load could be inductive. So that's another problem. I would explain why that's a problem. It's going to damage the switch. The output voltage, we don't want it to pulsate between 0 and VG. We want it to have a smooth voltage. As you see here, this is pulsating between 0 and VG. But what we want is, in ideal situation, we want it to be very smooth and we want it to be flat. And also VG may have AC components. That's another problem. If we are using a rectifier, then the rectifier itself creates ripple factors. So imagine that our input voltage is not a battery, it's actually a rectifier. That also creates extra problems and harmonics as well. So we have high switching harmonics, we have AC components, we have a pulsating. To fix these problems, we need to add different components to create different type of filters. The capacitor is added to store the voltage. The inductor is added to store current. As mentioned before, inductors are good for storing current. Capacitors are very good for storing voltage. And if we just add the capacitor itself, what happens is when the switch opens, you're going to have a high voltage at the end of the transistor of the switch, and it's going to damage. So we need to add the inductor to protect that. But also that creates another problem. So let's start with the topology and with the low-pass filter itself. Again, the inductor capacitor creates a low-pass filter. If we switch the position of the inductor and the capacitor and put the capacitor in series and the inductor in parallel with the resistor and the switch, we're going to have a high-pass filter. This here is a low-pass filter. How do we know that? If you put a DC, DC is going to pass, so you're going to have a low-pass filter. If I switch these two and the capacitor is here, the DC would not pass. DC is low frequency, zero frequency, therefore it's a high pass filter. Now, the output signal for this will look something like what you see in these graphs. So the output voltage would hover around the average voltage. Again, this voltage V out would be equal to D VD, or the input voltage. And the other thing that we have is the frequency spectrum. Are you familiar with the frequency spectrum? Fast Fourier transform. Did you pass signals and systems? Okay. So we have a time graph or time spectrum, and we have a frequency spectrum. And the frequency spectrum tells us how much of that signal is in a certain frequency. Okay. So for example, if I have a signal like this outlet, which is at 60 hertz, we don't care about the amplitude or anything. The important thing is just the frequency here, okay? Or let's say it's 120 volts and 60 hertz to make it easier. If I want to draw the frequency spectrum, if I do what we call an FFT or fast Fourier transform, we're going to have a peak at 60 hertz, okay? Meaning our signal has a frequency mainly at 60 hertz, okay? But if this signal is carrying another signal, let's say it's acting like a carrier for a 1 megahertz signal, which has a lower amplitude this time, and I'm going to show it with black, and this one has a frequency of 1 megahertz. Then in my frequency spectrum, I have another frequency, 1 megahertz, but it's smaller. Means that this signal is a combination of two signals. It's not a single signal. You have a 60 hertz and a 1 megahertz combined together. Okay, and when you draw this, it shows you all the spectrums, frequency spectrums. Okay. A Fourier transform is basically when you break down a signal to its building blocks, to its building frequencies. If I have a signal that looks like this, it may seem like a random signal, but with Fourier transform, we can explain that, okay, this is like this signal plus this signal plus another this signal. So we can break it down. This is, I'm simplifying, actually. It's more complicated than that. And if I show the frequency spectrum of this, this is like 60 hertz, this is 20 hertz, this is 10 hertz, then I would have a frequency spectrum that has a part in 10, 20, and 60 hertz. Okay. Now, In a DC to DC converter, we have the same thing. We have a pulsating DC, and also we have a ripple. And if I actually draw it, it's going to look something like this. And it's a combination of different frequencies. And these frequencies create what we call harmonics. And the harmonics sometimes damage the system. Usually the third and fifth harmonic is the most important one because it's going to actually intensify the output, and I'll explain more about that. But this graph over here just shows us the frequency spectrum, meaning the output signal is combined of different signals, which has different frequencies, and we usually have them at Fs, 2Fs, 3Fs, 5Fs, and so on. And the last one shows the logarithm scale, which is the output to the input, shows the output to the input or the gain of the signal. And you can see that when the frequency increases, you would see a drop in the output gain. And the reason for that, again, after a certain point, this acts like a low pass filter. It just cuts off every high frequency that you have. So over a certain frequency, you would have nothing in the output. Now, let's study an example. This is a converter, a 39 volt DC to a 13 volt DC. First of all, I want you to find the duty ratio for this. What is the duty ratio for this? The duty ratio for this, V out, would be equal to dVin. V out is 39, Vin is 13, therefore D would be what? Sorry, V out is 13 and Vin is 39 times 39. Therefore, D would be equal to 13 over 39, which is 1/3, or 33%. Now, the first thing that we want to do to create a practical buck converter is by adding a capacitor in parallel with the load. The reason is that we don't want to have a pulsating DC. We want to have a smooth DC and control the ripples. But in this particular case, because the voltage of the capacitor, when the switch is closed, what happens is the capacitor is fully charged. It reaches almost 13 volts DC. And when it's opened, and this, imagine if this is a transistor. When it opens, then you have a very high voltage in the emitter, for example, of the transistor. And what happens is the source current spikes and just burns out the switch. So again, you're going to have a huge voltage on the switch itself when the switch is open, and that's going to burn out our switch. Now, to prevent that, we add an inductor L. This would prevent that huge spike in the current because the inductor now is storing current. Okay? But now the inductor itself causes another problem. The problem that the inductor creates is that when the inductor is now fully charged, it has current in it. When the switch attempts to open, so imagine it's closed, when it wants to open, the inductor's current momentum results in a high LDI to LDT to DT and burns out the switch again. So when the switch is open, if we don't have an inductor, the capacitor is going to burn out the switch. When the switch is closed and we want to open it, and So the inductor now is going to burn out the switch. To solve this problem, we add another component, the diode, which acts like a freewheeling diode. So the switch can be opened and the inductor current can continue to flow. With high frequency switching, the load voltage ripple can be reduced to a small value. The higher the frequency is, again, I showed you in the previous one as well, you're going to have less ripple, but you're going to add to a loss when you have a high frequency. When you double the frequency, you're going to double the loss as well. And that's a topic for another part of the class. So again, we need to add the voltage, the capacitor, to be able to control the ripple and have, instead of having a pulsating DC, we want to be able to charge the capacitor. I'm going to show you the capacitor voltage with the black one and discharge it and make it having less ripples. But when we have this, the capacitor is going to create a huge spike in the current and it's going to burn the switch or the transistor. To mitigate that, we add a inductor, and this inductor acts like a current storage system. But the problem is, again, if I add the inductor when the switch is closed and you want to open it, it's going to again create a huge spike and burn out the switch. To add this problem, we add another component, the diode, which acts like a freewheeling. It allows the current to pass and prevents a huge spike in the current, therefore the voltage, and it's going to prevent the switch from burning. So just to summarize, adding the capacitor creates a huge surge in the current. Adding the inductor creates a huge surge in the voltage. LDI dt is the voltage, technically. And adding the diode controls the current voltage and prevents it from burning. So KCL, KVL, and steady state KCL applies as follows. The instantaneous sigma of all the currents would be 0. The average would also be 0. In steady state, also KVL applies, meaning the instantaneous summation of the voltages is going to be 0, and the average is going to be also equal to 0. Now for the inductor current, this is an example of a switch with the inductor capacitor low pass filter. I'm going to call it the LPF. And the diode, which acts like a freewheeling system. This graph over here shows us the voltage. This is the voltage graph. The second graph shows us the current. T on is when the switch is closed, and VD is applied to the input. And T off is obviously when this is opened. I'm going to show it with the open circuit. And we don't have anything in the input of our system. Now, the important part that we want to study here is the inductor's current. When the switch is closed, the current slowly increases. When the switch is opened, this current starts to decrease, but you can see that it doesn't drop to 0 because it's storing the current and you have a little bit of, current stored in the system, therefore it's not gonna drop to 0. As mentioned before, the average voltage would be somewhere around here, which is our V output, And the average current also is going to be at the average that we're going to have, which is higher than the higher than 0 and lower than the maximum current that we're going to have. And this is going to be I output, which is the average current as well. So step down converter circuit states, assuming IL flows continuously. In picture A, the switch is on or closed, and in B, the switch is off or open. Now let's study the inductor current slope. So when the switch is on, again, we know that VL, the voltage for the inductor, is LdI dt over dt. L doesn't change, it's constant. So changing the current changes the voltage. So when the switch is on, meaning at this stage, you can see that this is when it's on. When you are calculating the derivative, what does derivative mean in the graph? Means we have to find the slope, okay? So here we're going to find the slope here, the alpha. So again, this slope is important for us. And this slope gives us the derivative of di over dl. Now, this would be 1 over LVL, which is going to be Vn minus V out over L. So the switch, when the switch is on, di over dt is going to be Vn minus V out over L. And when the switch is off, again, we have to find the slope here, which is going to be, again, negative V out over VL. So this, again, is when the switch is on and when the switch is off. Okay, now let's solve a problem. We want to find VL when L is 2 Henry, Vn is 5 volts, and V out is equal to, let's say, 1.2 volts. We want to find VL on and VL off. I'll give you a few minutes to think on this and solve it. So where is it when VL is on? Yeah, I think it's going to be Vn, which is 5, minus V out, which is 1.2, over L, which is 2. So 5 minus 1.2 gives us 3.8, divided by 2 is 1.9. And for when it's off, it's going to be negative V out, which is negative 1.2 over L, which is 2, so negative 0.6 volts. Did you get the same?
So, I guess when you're solving VL on, you're just using the what 1 over LVL.
Yes.
You're not incorporating.
No. I want to find the L, the I over DL one. Yeah. If you want to do that, yeah, you have to incorporate that. It's going to be divided, and that technically gives you just V out of the system. Okay. Now, the thing is here, we want to find, the important part is actually we want to find this delta V, the difference, or delta I, let's say delta I L. We want to find how much is this changing and how much is the ripple in the system. So the inductor current ripple, the IL waveform is symmetrical about I. Hence, during the first subintervals, the current increases by 2 delta IL. So again, from here to here, it increases by 2 delta IL. And delta IL is between the maximum and the average. So this is delta IL. So from here down to here, we would have 2 delta IL. And the change in the current is the slope times the time length of the first subinterval, or DTS. Therefore, 2 delta ILs would be Vn minus V out over L, which is the slope, times DTS, which is the time length that we have. Do you remember what DTS was? D is equal to T on over Ts. Therefore, DTS is equal to what? T on. And you can see here it's when the switch is on. So instead of this, you can also write T on. And this is equal to 2 delta IL, because this is 2 delta IL. And if I want to find the delta IL, it's going to be Vn minus V out over 2L times DTS. I want you to write this down. We're going to have a question on this. Now, the inductor's volt-second balance system, initially when you turn on the switch, the output voltage and the output current, initially and the inductor current, everything starts from 0. So it slowly goes up until it reaches a steady state, okay? Because initially all the storage elements are empty. You have to charge your capacitor, you have to charge your inductor. So initially your current starts from 0. So the moment you start the system, it didn't have any power before that, it's going to be starting from 0. It's going to go up until it reaches its steady state. This is the average that we're going to get. So you can see that if you follow this, it's going to start from 0 and you're going to have this steady state going on. Is it clear? Okay. So in steady state, the average voltage across an inductor is 0. Again, because we already know what this is from, I think, in measurement instrumentation, I already mentioned that for an inductor, it's storing currents, the average voltage is always equal to 0. And we can prove that using the equation VL is 1 over Ts, the integral of 0 to Ts VL dt, which is going to be equal to 0. VL would be L di over dt. And if we calculate that, it's going to be 1 over L 0 to Ts VL dot dt, which is going to be equal to 0. Therefore, IL Ts minus IL 0 is going to be equal to 0. But if we want to find the VL at each point of the time when it's turned on, VL would be equal to 1 over Ts 0 to dTs VL dot d tau plus the integral of dTs to Ts VL dot d tau. This is for when it's turned on, area A, and area B when it's turned off. When this turned on and when it's turned off. And that would be equal to V is equal to dVn. The capacitor amp second balance, again, the same thing. A capacitor is charged for charging and storing voltage. The average current for a capacitor is going to be equal to 0. So IC is 1 over Ts, the integral of 0 to Ts IC dot dt, which is 0. We also know that IC is C dVc over dt, which is again going to be equal to 0. The same thing, VCTS minus VC0 is going to be equal to 0. And the same thing that we did for the current of the inductor, we can expand it for the voltage of the capacitor. To find the voltage of the capacitor and the average voltage of the capacitor, we need to find the average charge of the capacitor. And as you remember from the capacitor's equation, Q is equal to CV. In other words, Q is equal to C delta V. Now again, what happens in the capacitor? The capacitor is charging up, so the current is going up, and then it's discharging. So charge and discharge cycle. And the charge that is accumulating in the capacitor is equal to C times this times the delta V that we have. And this is the voltage graph for it. So C times delta V gives us the average, the charge in the capacitor. By the way, I have to mention, we have assumed that the inductor capacitor here are ideal. Non-ideal, you have a very complicated situation. You're going to add the internal resistance and so on. And it's making minor changes in the system. The only component of output capacitor current is the one rising from the inductor current ripple. The capacitor current waveform is equal to the inductor current ripple. By the capacitor relation, Q is equal to CV. The area of the shaded triangle, Q, or delta Q, the amount of charge changing, is going to be equal to 1 over 2 or half of delta IL over 2, Ts over 2. Again, because this is half of delta IL. Because the current, we assume they are ideal. The same current that goes through the inductor is passing through the capacitor. Therefore, the voltage ripple delta V out is going to be delta IL Ts over 8C. 2 times 2 times 2 is equal to 8. And it's equal to, and by the way, Q is equal to CV. So this C goes to the denominator. And for delta IL, we had V out 1 minus D Ts over L, Ts over 8C, which is going to be delta V out over V out. which is going to be half of pi square 1 minus d fc f over fs square, where fc is equal to 2 pi square root of LC. This is for the low pass filter that we have, the cutoff frequency, what we call it. So the switching analysis in a DC steady state, again, I want you to write down this equation, which is very important. And one thing to keep in mind is delta V is related to FC and FS. FS is our switching frequency, and FC is our cutoff frequency. The higher the switching frequency is, the lower the delta V would be. The higher the cutoff frequency is, the higher would the our delta V be. And I've added an explanation here. Hence, inductor current ripple cannot be neglected to calculate the output capacitor voltage ripple. To reduce the voltage ripple, yet one, we can increase Fs of the frequency, the switching frequency, or we can reduce Fc. This is not affected by the load output resistor. Again, to reduce the voltage ripple, which is delta V, again, we want this delta V to be the lowest. We can either increase Fs or we can reduce Fc. We want this ripple to be something like this, like very close to the average, because the closer they get, you have a better, DC signal. So we want it to be a smooth DC. Sorry, just give me a second to fix this. My pen stopped working, so I have to connect. So switching analysis in a DC steady state, we have V out is going to be VA, dVn. We have delta IL, which is Vn minus V out over L dTs, or in other words, V out over L1 minus dTs. IL is equal to I out, which is V out over R, V naught over R. Vn In is V out, I out. Why? Because we would assume that this is an ideal situation, and Pn is equal to P out. And In is equal to DIL, which is DIO, DI naught as well. Again, because we had assumed that this is an ideal situation, we don't have any loss in the system. Now, we're going to have just this one quiz today. And the quiz is that for the online students, we're going to have a different quiz. I'll post that quiz. In a step-down converter, Vn is 20 volts, V out is 12 volts, and the switching frequency is 400 kilohertz. This converter is operating in its continuous conduction mode. Calculate the time period during which the diode is conducting every switching cycle. Give you some papers. Again, this is for attendance. Thank you so much. That's it for the online students.